Welcome to this presentation about flow in long subsea gas pipelines. We will discuss how it works, basically how it flows, and we will do so by simulating one of the world's longest subsea gas pipelines, the SeaPipe 1 pipeline. This is a map showing some of the pipelines in the North Sea. We see the Norwegian coast here, and we see the British coast here. Here is Belgium, and here is Sleipner, one of the oil rigs at the in the Norwegian sector of the North Sea. And we are going to look at the SeaPipe, which is this pipeline here. It's 814 kilometers long, and it was by far the longest when it was commissioned in 1993. This is one long pipeline, one stretch. There's absolutely nothing in between Sleipner and Zeebrugge in Belgium. No valves, no platforms, no compressors, nothing. The pressure can maximum be 14.9 megapascal at Sleipner. The pipeline isn't certified for higher pressure. In the receiving end, the customer has a guaranteed minimum pressure of 8.3 megapascal. So that's what has to be satisfied at all times. Some interesting questions we will discuss is the transport capacity the same summer and winter? And what happens to the capacity if the pipeline gets buried? Sometimes it can be wise to bury it to protect it from anchors or other things, and sometimes it gets buried unintentionally due to sand forming on top of it after a while. We will discuss the fact that it also affects the capacity of the pipeline, how much gas you can push through it. Also, sea currents, they also affect the capacity. And we will look at how engineers do their calculations, or at least should do their calculations, and discuss how accurate calculations are possible with today's technology. It will probably come as a surprise to some engineers that at the design stage of a pipeline, our calculations aren't quite as accurate as we like to think. Here is a cross-section of the SeaPipe pipeline. We see that the innermost layer of the pipeline is made of steel. It's around 30 millimeters thick. It varies slightly. And at the outside of that, there is a layer of about 6 millimeters of coating. That's to protect it from corrosion mostly. Then there is a thicker layer, outermost layer, that is weight concrete. The purpose of that is, as the name says, to weigh it down so it becomes more stable. It doesn't move so much due to sea currents, for instance. We have now started a simulation program which we will use to investigate the flow in the SeaPipe line. This simulation program is called Flowline Pro. It can simulate single-phase flow where we have only gas or only a liquid, and it can also simulate multi-phase flow, for instance a mixture of oil, gas and water. But we will use only the single-phase part of it now. And we will only use a steady state simulation. The transient simulation will be done in a second video. So let's define the case we are going to simulate this time. Let's call it the SeaPipe gas export pipeline. And we can add a subheading also if we want. We can say this is steady state. simulation of, and we will go for the coldest month because the different months have different sea temperatures. And the PVT properties, we have to tell the program which PVT properties we want to use. They are things like density and viscosity and Prandtl numbers and some other parameters as a function of pressure and temperature. In this case we do it the simplest way. We have prepared a file where these data are located. That file is created in this case by another program called PVT sim, and we just read those data from a file as we simulate. We also have a built-in PVT program in Flowline Pro, but this time we choose to use this file. Okay, then we start drawing something here in the canvas. I right click and I can add a line. That's the first thing I can do. So I just draw my pipeline here. And then we have only one pipeline, so that's very simple, but I have to give in data for this line. So I double click on it, and then he tells me which data he needs. So I need to know in a lot of points along the line. This is distance from inlet. Obviously I start at the inlet, which is 0 distance, 0 meters from the inlet, and then I put in lots of values down here. And for each of those points along the line I have to tell the program what the elevation is, basically compared to sea level. We start around 40 meters above sea level. The diameter is slightly less than a meter in our case. The roughness, I can go to a table and I can double click here and get some advice for roughnesses for different types of surfaces. But in our case we don't need to use this because we have actually measured the roughness. So here we are, the roughness, and also the surface uniformity factor, which is something described in some books I will give a reference to at the end of this video. We need to tell the simulation program about each layer's properties. For instance, the inner steel layer, we need to tell him how thick it is at the various points along the pipe. Needs to know the thermal conductivity, that's how well it conducts heat from the gas and out to the seawater. The elasticity, the elastic modulus, outside temperature, how deep it is buried, the soil properties also. This pipeline is partly buried most of the way and fully buried in some places. The outside sea current also must be given. Outside airspeed is obviously not relevant for a pipeline which is submerged. Now I have prepared many of these data already. It has been done a survey on this pipeline where we know how deeply it is buried at various points along the line, and those data I will just paste in from the survey and into the pipeline here. Before I do that, let's notice that there is something missing. This pipeline had actually 3 layers. Here only 1 layer mentioned. So I add some more layers here. Add new pipe layer, there's layer 2, and there's also a 3rd layer, add pipe layer. And I just paste it in. So there we go, there are all the data of relevance to the pipeline. We see that the airspeed is 0, the outside diameter, the sea current is given here, and some quality for the soil. That can be also proposed in here for different types of soils. We can double click and it can show us what the thermal conductivity is for various types of soil. And there are suggestions we can come up with for other parameters. Okay, let's accept this. So now we have specified the pipe. But we also need to tell the program what we have at the end conditions. So I right click and I add a boundary here, and I add the boundary at this end also. I double click it, and up comes a menu which allows us to tell the program what, for instance, at the inlet end I choose to specify the pressure. So I have a known pressure there, and that pressure is 14.9 megapascal, so that's E6 Pascal, and I set the temperature to 288 Kelvin, and we can insert more pressures here. If it varies over time, we can have different points in time, but since this is steady state simulation, we do not vary anything over time. That's the definition of steady state. Everything is constant over time. So we accept that one, and we have to do something. Hey, what is this? Here came that was, I inserted a line accidentally instead of a boundary. So let's insert a boundary again here, boundary 2, and then I go and specify what we have there. It's still only single phase, and then I choose to have an external flow there, the consumer, and the type of flow I can choose between velocity, volumetric flow, and mass flow. Mass flow is most relevant because the consumers down in Belgium, they need a certain amount of kilos of gas per second in order to heat up the houses and whatever else they do. So the mass flow is the most relevant parameter. And I'm going to study a day where they use 382 kilograms per second. The temperature always needs to be specified, even though it doesn't necessarily, well, it clearly doesn't matter in this case because the gas flows out in this end, not in. So the temperature outside of the pipe is only relevant, obviously, if it flows into the pipe, which it doesn't do at the outlet end. So it doesn't matter what I specify, this number isn't going to be used by the simulation program. So I accept this. So now everything is set up. Let's go ahead and simulate. Steady state simulation. Here we go. We see the line down here showing the progress. And there it has completed. Let's save this also, so we have it for later before we start plotting anything. So I save this case. I can just call it whatever. I can call it, for instance, sea pipe coldest month, because the sea temperature I put in here was the coldest month temperatures. I save it. And then let's start plotting something. Let's look at the elevation profile first. The pipeline starts 40 meters above sea level, and then it goes straight down to the seabed, 80 meters below the sea, and it gradually rises to around 40 meters, and as it comes in here at landfall in Belgium, it's obviously above water again. We can look at the burial depth also, which, as I said, was determined by a survey. A submarine was running over it to see how far it was buried. Near the inlet, it wasn't much buried. It's around, let's say, 20 centimeters here. So it's only the lower side of the pipe is only 20 centimeters into the seabed. But once we get closer to Belgium, it is lying lower. It has been buried somewhat by sand. And here, for instance, it's fully buried. We can also see the outer diameter. And when it's buried more than the outer diameter, then clearly it is fully buried. So here in the midsection, it's mostly fully buried. And near the outlet, it's also pretty much fully buried. The pressure along the line near the inlet, the pressure was 14.9 megapascal. Then it increases a bit as the pipe goes down to the seabed. That is logical because we get the static head when we go down towards the seabed. But then friction makes the pressure fall gradually towards the outlet. And it comes down to, let's hold the pointer over here, 82.8 megapascal is the pressure here by the outlet. So that's just above what it needs to be to satisfy the guaranteed minimum pressure at the receiving end. The temperature can also be interesting. This is the gas temperature. It falls quite fast at the beginning and then it falls more slowly. Now how can that be? Well, let's look at the sea temperature also. This is a typical sea temperature for the coldest month of the year, averaged over many days and many years even. And we see that a short distance into the pipe, the gas temperature has fallen down to the sea temperature. Partly because the sea cools the pipeline's outer side and that cools the gas. But we see something interesting happening after the gas has become as cold as the sea temperature. The gas temperature continues to fall. And that happens because of something called the Joule-Thomson effect. That's something that happens only with non-perfect gases. Real gases behave in a different way than the simpler ones we learned about at school, the so-called perfect gases. So when it expands, even though there is a friction that in a way should heat the gas as much as the temperature falls when it expands, that doesn't quite balance each other, so the temperature continues to fall. So we see the temperature becomes lower and lower towards the outlet. We can also plot how much heat is given off per meter of pipe to the sea. Or rather how much heat comes from the sea and into the pipe. We see it's negative at the beginning. It means heat isn't coming from the sea into the gas, but opposite, gas gives off heat to the sea. And that becomes zero when the sea temperature and the gas temperature is the same. And after that, heat comes from the sea and into the gas. This is something we would rather avoid, of course, because when the gas is heated, it expands, it gets a lower density, and that means higher friction, because the velocity will then become higher than it would become if it was colder. So in this case, thermoinsulation would have been a good thing because it would prevent the sea from heating up the gas. While in this part, thermoinsulation would be a bad thing, because it would prevent the sea from cooling the gas, which we would want the sea to do. We can also look at the velocity. The velocity starts out at this value, a bit more than 3 meters per second, and then it falls because the gas cools down, the density goes up, so even though the mass flow is constant, the velocity goes down because the density goes up. But then, as it expands towards the outlet, we get more and more, the velocity gets higher and higher because the density goes down. So the gas expands towards the outlet and the velocity goes up. We can look at the density as well. Here we see the density reaches a maximum after it's been cooled, and the density goes down as the gas expands towards the outlet. The Reynolds number is quite high for a high pressure pipeline, even though we have very low velocities here. We can see that the Reynolds number is around 36 million here, which is higher than the Moody diagram. The traditional Moody diagram doesn't cover that. The measurements the Moody diagram is based on, the diagram most people use for calculating the friction, doesn't really go up to these Reynolds numbers. So we have created a new Reynolds number, which you can read about in the books I'll give a reference to later in this video. The friction factor, the Darcy-Weisbach friction factor, also varies a bit along the line. So that has to be recalculated and at every point along the line. But it doesn't vary very much, as we can see. So now we have an idea what happens at winter time, because we used winter sea temperatures in these simulations. It's of course interesting to know what the typical summer month would bring also. Let's go back to the original flow diagram. Here we go, and then we go into the pipe data again. I double click here, and then let's go to where the sea temperatures were given. Here we go, T ambient, and I now paste in the temperature profile, which is typical of of summer temperatures. I've copied that from an Excel sheet where I have those data, and I paste it in here. Then I say OK, and I do the simulation again. Here goes the simulation, and there it's finished. We choose a new tab, and we we plot the pressure again. Now this is the same pressure as we simulated at first for winter temperatures, but a new tab has appeared here, and that's where we will find the results for the last simulation, which was summer temperatures. So now I also print the pressures for the summer temperature. And now we see, although we start at the same pressures, we have the same mass flow as before. But we see that we have a much larger pressure loss now. The pressure we arrive at down in Belgium is now, the minimum pressure occurring here is 7.7 megapascal, whilst before, during the winter, it was 8.3 megapascal. So this shows that if we continued in this fashion, trying to push as much flow through the line as we did in the winter, we would end up with too low pressure down in Belgium. So the sea temperature had an effect. But luckily, the effect was such that we have highest capacity in winter, and that's also when we need most gas in Belgium. That's when they have to heat the houses more because of the colder winter temperature. We can also compare the temperatures. First, let's show the temperature as it was. This is the gas temperature during the winter, and the last simulation was for summer. So we add that curve to it, and we see that temperatures of the gas will be much higher than. Well, much. It's not that big difference. Well, 10 degrees or something like that, difference between those two curves. We can also show the ambient temperature here, the sea temperature, and we see that during a typical summer, hottest summer month, it follows this blue curve, while the gas in the pipeline follows this curve. While during winter time it is quite much colder, and that explains the difference here. What if the pipeline wasn't buried at all? We can go back again to the flow diagram and go ahead and say that the burial depth is 0 everywhere. Here is the buried depth, and I paste in only zeros here. I accept that and I resimulate. So the most relevant simulation to compare with now would be pressure, because now it's summertime on buried pipeline. Here is the pressure for summertime buried pipeline, and the last simulation was unburied pipeline. And here we see the comparison. So that didn't have a huge effect, but it has some effect. In a pipeline with such enormous money flowing through it, this is actually significant also. So we saw that once it wasn't buried any longer, we had a higher pressure loss along the line, and it arrives then at a lower pressure down in down in Belgium. We could compare the temperatures also. Here are the temperature for summertime when it's partly buried, the way it actually is at the moment according to the survey. And here is the temperature as it would become if it wasn't buried at all. So we see it's a considerably higher temperature in the gas if it isn't buried, because it gives off more of its heat to the seawater then. So being buried is actually a good thing for this pipeline because it acts as insulation. It's also interesting to see what influence the surface has. We remember the internal surface roughness of the pipe is one of the input parameters. So let's reset this and go back and change the surface roughness also. This is the one, here we go, we have 2.23 10 to the power minus 6 originally. Now suppose we double this, so the surface roughness is double this in the whole line. That I just paste it in here. Now I have doubled it. This is still a very, very smooth surface. So it's still very smooth, but let's see what effect it has to double the very moderate unevenness which is already there. We say OK here and we simulate again. New plot, and we go to the pressure. What is relevant to compare against here, I would say, is the last plot we did. It was pressure along the pipe at summer for an unburied pipe. Now let's compare that to the pressure in the last simulation, which was with a doubling of the surface roughness. And we see that has a very significant effect. So we are talking about the pressure loss in a ultra smooth on a pipeline compared to one which is only slightly less smooth. It's still very smooth here. And we get a much higher pressure loss. So that's very significant. And we wouldn't be able to keep the contract in this case. Well, we already had a problem at summer temperatures for this very high mass flow that we have been focusing on in these simulations. It can be convenient to generate a report also and look more closely at some of the data there. But now we have so many different plots here, so we don't want to make a report of all this. I simply close the whole program at first, and then I restart it, and then I just reload the case. Remember, we saved the case, so I now reload the existing case. Here we go, and let's replot the things we have plotted already. We plotted the elevation profile, we plotted how deeply the pipe was buried, we plotted pressure, temperature, and also sea temperature. So now we are back to the winter month and the actually buried pipe the way it was originally. We can plot the velocity, maybe the heat loss per meter of pipe, and we plotted the Reynolds number, friction factor. We probably did not plot the diameter. Let's do that also. Here is the original pipe diameter when it isn't pressurized, but once we put pressure on it, it expands somewhat because the pipe wall is somewhat elastic. It isn't expanding a lot, but it is enough that we need to take it into account when we want to make very accurate calculations, because the increase in diameter means the friction goes down, and it also stores more fluid in there, and it has an effect on how the transient simulation behave, which we aren't focusing on in this case, but even for friction in a steady state case, it has an effect. We can generate a report. We make a full report in this case. And there came the report. For the sea pipe gas pipeline, as expected. And we see some of the data here. Make it a bit larger. The average velocity when we ran at full capacity here was 4 meters per second. That was the average gas velocity. So the transfer time of the gas, the time it takes from it's put into the line till it comes out at the other end, is 56 hours, it says. So that's a bit more than 2 days. The composition, what the gas consists of, is practically no water, nitrogen or CO2. The percentage of that, the mass fractions of that are very low. But there's a lot of methane, ethane and propane, mostly methane, which is what natural gas typically consists of for the most part. And there are some slightly heavier components here, but the really heavy components have of course been taken out during the refining process, so that it's only light gas. It won't condense and become partly oil or anything like that during its journey down to Belgium. And then we get the plots also in here. The plots we just chose will be in the report. And this report will be uploaded to the internet site, so it's possible to go and pick this up from there. Here are some of the parameters affecting a pipeline's capacity then. The most obvious one is obviously the pipe's inner diameter. A larger pipe can clearly transport more gas than a smaller one can. The pressure in the line also plays a part, because if you have higher pressure, you force the gas to take up a smaller volume, if you like. The density goes up, then the velocity goes down for the same mass flow, and that means higher capacity. So high pressure pipelines have generally higher capacity than low pressure lines. Available pressure loss also plays a part. The higher the pressure at the inlet and the lower the pressure at the outlet, the more available pressure loss you have, and the pressure loss is what pushes the gas through the pipeline, obviously. You simply counter the friction in there. For the most part, it's friction that matters. The inner surface of the line also plays a big part, and it makes sense to put a lot of effort into making the surface very, very smooth. There's actually a considerable difference between extremely smooth surface and only very smooth surface. So extra coating or other things to make it smooth is generally a cheaper way to increase capacity than by increasing the diameter. The gas composition obviously plays a role also, but export gas doesn't vary extremely much, so I put that only at the fifth in the importance list I have created here. Sea temperatures plays a role. The colder the sea, the better. Sea currents also play a part, but that which part it plays depends on whether the sea is hotter or colder than the gas. You want the gas as cold as possible. So if the sea is hotter, then high sea currents is bad, because it gives more intimate contact between pipeline and sea, and so heats the gas more, and vice versa. If the gas is hottest, then being cooled by the sea is a good thing. Thermo-insulation affects it, and again, whether it's a good or a bad thing depends on whether the sea is hottest or the gas is hottest. And of course, here I include any thermo-insulating layer, whether it's meant for thermo-insulation or meant for, let's say, weight concrete to weigh it down. Burial also, same category again. Whether it's good or bad for capacity depends on the temperatures we are faced with. And the elevation profile plays a part, but typically not a very dominant part. And we can't do much about it. We have to follow the seabed whether we like it or not. Now here are some claims about calculation accuracies. At the design stage, the by far most important parameter affecting how accurately we can calculate the capacity is how accurately we know the friction factor at the inside of our pipeline. And the tabulated data aren't very reliable, and also the traditional Moody diagram isn't very good. It depends on what your Reynolds numbers are, because the Moody diagram is more accurate in some areas than in others, and depending on where you happen to be in the Moody diagram, your accuracy can actually be as poor as up to 12% for gas pipelines. So that's really something to be looked into if you are designing a very expensive pipeline. These can of course cost billions of dollars to create and to operate. During operation, the accuracy is, you typically have more data than you have experience with what the pressure loss is in your pipeline. The instrumentation will tell you that. But your accuracy will then depend on how well you use those data which are available, and also whether you have available reports for sea temperatures and currents. So I've said the inaccuracies can be up to 3%, but it can of course be even worse if you do not manage the data you have properly. The look ahead accuracy, which is by look ahead we mean using the simulation program to predict what the capacity will be some days from now, let's say. That's very much in a similar category. If you know what the temperatures will be, then you can get down to around 1% in accuracy only. But again, it depends on how well you use the data which are there and which simulation software you have. Of course, having very accurate operational and look-ahead accuracy is important when you sell capacity for the pipelines. to utilize it maximally, you want to be able to calculate very accurately, and it's a lot of money involved in doing that right. The main conclusion from the simulations we have seen, maybe we can summarize it as follows. Best design and operational practice requires great care. There are many parameters we have seen affecting the line's capacity. Some of them not quite as obvious as that we would even think of them normally. And intelligent use of available data is important, and of course all the calculation has to be done by simulation software. It's way too difficult to do it manually. If you want to read more about it, you can go to this internet site and download free copies of the CPIPE report, which was created when recording this video. And there are also 2 books there. They are also free and can be downloaded free. And all the theory used in the simulation program is described there, and a lot more theory also, including multi-phase flow, which will also be shown in another video, which you will find at the same internet site. I hope it has been useful. Thank you very much for listening.